So thank you very much, Ganesh, for that introduction. And so yes, I'm going to, and to the organizers, of course, the other organizers for inviting me. So yeah, I'm going to be talking about mean field games, which is currently an extremely active area of research. I'm going to start in this lecture with a very, the sort of simplest instance of this problem and show how it already leads to some interesting questions. Okay, so what is the motivation? Is that in many applications, you have a whole collections of many homogeneous agents that compete with each other. And I will explain all these terms. So of course, many of you might know a common notion of equilibrium when they're competing with each other is something called the Nash equilibrium. But in general, Nash equilibria are hard to compute in games with even a moderate number of players. And there's a whole literature actually on the computational complexity of Nash equilibria with people like Daskalakis, Papadimitriou, etc. I'm not going to talk about that. And also in general, Nash equilibria are not unique. So if you're interested, this is even when you have a moderate number of players. So sort of what do you do to try to understand what these systems would look like? So maybe somewhat counterintuitively, but you actually look at the case when the number of players is large. But there's a subclass of games where you can say something a little bit more. So like I told you that it's computationally intractable in many cases, and you can show that it's NP hard to even approximate and sort of in the general case. So what you really want to do is maybe see whether there are subclasses for which you can get nice approximations. And one that really arises much in practice are what called Nash equilibrium games with a large number of players where the games are symmetric, and I'll explain exactly what that means. This is just the high-level introductions. And they're of mean field types, in which case either the dynamics and the sort of the specification, the data on the model, and how each agent behaves and how it depends on all the other agents, because the whole complexity in the system comes from the complex interaction between different agents. They depend on the others only through in some sort of mean way, in the sense that it only depends on the fraction of the players in different states, or the empirical measure of the states and the actions of the other players, rather than the detailed identity and of each of the players. So it turns out that instead you sort of look at these class of symmetric games, and then there's quite a nice theory there where you could take the limit n to infinity and you want to try to understand if you can, in the limit, do things simplify? Does it become more computationally feasible, or to qualitatively or quantitatively understand what these limits are? Okay, so that's sort of the basic idea behind mean field games, and I'll get to specifics. So many people, you're interested in sort of dynamic games where people are moving and reacting to each other, but today we're just going to be talking about static games. So where do these static games arise? They arise in a number of places where algorithmic game theory, congestion games, I'll define both of these things. So of course, the simplest static game, not necessarily of the symmetric type, would just be sort of auction games. Everybody has to just decide what price they're bidding, and then you take the highest of all of these. So this is also a game where people are interacting. And there are certain things called European auctions in which you can sort of dynamically bid prices, right? So that would be sort of a dynamic game where you sort of are reacting to how everybody else is bidding and then bidding. So these are sort of ubiquitous. So now let me tell you a particular example of a congestion game, which is involved in network routing and traffic control. So consider a network, maybe you have 4 nodes in this case, in which different traffic needs to flow between various source-destination node pairs. Okay? And please feel free to interrupt me at any time. This is informal. So each agent chooses a particular route between the source and the destination so as to minimize the congestion cost on the route. Okay? So there are some congestion at each node, and you have to choose something that's... And the congestion cost will depend on the aggregate number of other users on that route, right? And so one question you might want to ask is, okay, you know something about how many people want to go to each destination, and everyone is trying to minimize their congestion costs. What does the network look like? So that's like a very natural question. And you want to say, in this, it's natural that what you would when people are playing like this, they would not try to do something different if they're in a Nash equilibria, okay? So I'm going to explain all that. But this is just to tell you one motivating example that you have at the back of your mind, and we'll come to it right at the end of this talk again, okay? Okay, so, but now let me tell you sort of the abstract framework first of static games. So in general, that was one example. So how can we sort of abstract, and I'm going to abstract it in an even simpler setting, in fact. So first, let's say you just have n agents or players, and you have each agent that chooses an action from some given set A, right? So in that case, your action would be sort of which route you take, okay? But okay, you choose from a given set A, which is called the action space, and throughout, I will assume that A is a compact metric space, okay? Right. And then often just finite. So it's fine to just think it's finite, okay, in many cases. Okay, and each agent has an objective function, ji, which depends on the total number of players as well as its own identity, which takes the actions of all players and then, maps it to some value in R, which is a certain reward, which could be positive or negative, to every possible strategy profile of everybody in the system. And the goal of the agent I is to choose its action so as to minimize the JIN. So it's able to see the actions of the other players, so it knows what or at least it gets the reward, knows what the JI function is, so as to maximize the reward, okay? Of course, in some cases, it may be more natural to say minimize, for instance, in a congestion, but you just simply put negative for the reward. So I'll just say maximize throughout. And now the optimal choice of agent I depends on the actions of the other agents and vice versa, right? So what you're led to is a coupled system of interdependent optimization problems. And so how do you resolve how they get optimized? And that's where the concept of a Nash equilibria comes in. So a concept that resolves these interdependent optimization problems is a strategy profile such that for every I and every possible other action. That is, the idea of a Nash equilibrium is that you're in a state of strategies, or the agents are in a state of strategies that's such that no one agent can unilaterally increase its utility or objective function by just changing its own action. Okay, so that's what this is saying. So the way to formalize this is saying if I change the action, my AI to A tilde, I'll only go down or not be any better off. Okay, so A1 to AN would be a Nash, the strategy profile would be a Nash equilibrium if changing AI for the objective function doesn't increase its objective function. This is just a static one shot. That would be a dynamic game in some sense, yeah. So we'll be talking about sort of continuous time dynamic games later, but this is just to start with the static game. Okay, yeah, you can talk about repeated games and many other different versions. Okay, and sometimes it's useful to think of an epsilon Nash equilibrium as a similar thing, which is that at most you could only increase your reward by unilaterally changing your action only by epsilon. Okay, so that's for everyone. Any one person, cannot change for more than epsilon. So that's the definition of an epsilon Nash. And then I said we want to consider a subclass of games which have some symmetry properties. So here you assume there's a common payoff function of the form, some function which takes the action space and also probability measures on that action space, which are going to represent the empirical measure of the actions of all the other players. Remember I said that you want to be symmetric in the actions. The way you depend on all the other players is symmetric, so you can encode it in terms of its empirical measure, right? Because it's permutation invariant if you change. So the N agent, the objective function is given in this particular form. It depends on its own action, and it also depends only on the empirical measure. This is just a delta mass at AK, which in a finite system is just saying the fractions of people doing different actions, right? Okay, and also here, as you can see, that you're assuming that they all have the same sort of dependence. So it's also homogeneous and symmetric, right? So, okay. And this is the symmetry property that I said that it doesn't matter, it's permutation invariant. The objective functions are permutation invariant in this specific sense. Okay, is that clear? This is the general framework. Any questions? Okay, So some of the standing assumptions I'll make before I can state what kind of results you may hope to get in this setting is that this function f is jointly continuous here now, where this PA will always be the probability space of probability measures on this space, right? And where PA is equipped with the weak convergence topology on PA. So which is just that if mu n converges to me if integrals against bounded continuous functions converge, right? Okay. Okay, so that's just jointly continuous, and this which is quite a simple assumption, not too stringent. Okay, and so now we want to take, why do we expect that large symmetric games will somehow have a nicer property? So here's some intuition before you state the result. So when n is very large, if you see how much this person depends on any other person, it's really of order 1 over n. So you expect some sort of decoupling to happen between different players. Okay, so when n is very large, any one agent does not influence the empirical measure much, right? Because you have this 1 over n. And so you expect the optimization problems to decouple, and with the homogeneity, then you expect sort of there to be the typical behavior. So all of them sort of are having the same sort of behavior. And so then if you think, well, there's going to be sort of some empirical measure limit, which is sort of the background of what everybody does, and then you also want to understand what you do. So there's going to be some relation between what you do and what everybody else has done, which is dictated by the Nash Equilibria. So you can probably write something just for a typical player rather than look at the whole complex system, right? So decoupling and just looking at the individual system and trying to formulate that explicitly is what one expects in the mean field. You have a question? Yeah, because most of them can be written as a function of the empirical measure, but even if you, yeah, that's really the point, yeah. You'll have to look at the details in terms of continuity properties, et cetera, if you have a different permutation invariant function, but yes, that's the idea. Okay, any other questions? Okay, so as I said, what the idea is, if you take n infinity, can we develop a suitable asymptotics for the Nash Equilibria of symmetric n-player games? So I think probably most of you do, but just in case. So just remember that if you take a nice space and a probability measures on this, you equip it with the weak topology, then when we talk about convergence, you want to know when things are relatively compact, which means subsequential limits converge. So then you say that a sequence is relatively compact if and only if it is tight. So there's a criterion, right, of relative compactness of probability measures, and the tightness has a nice, the way to check it is that to see that for every epsilon there's a compact set such that most of the mass is sort of uniformly, with all respect to all measures, is concentrated on that compact set, right? Okay, so this is just something that we might use from time to time for convergence results, okay? Okay, so in particular, you can see that if your space itself is compact, right, then obviously you can choose the space as this K, and that's going to always be 1. So automatically, any sequence of probability measures on that will be tight, okay? So the space of probability measures on a compact set itself is compact. Okay, that's what it tells you. That's a useful thing to keep in mind. Okay, so another thing that we will, I think, of course, with Jose's talk, must be used to the Wasserstein distance, but just a quick review. So if you have a Polish space, the space of probability measures with a finite pth moment, then you look at just, yeah, this is just the space with a finite pth moment. The Wasserstein is defined in this way, which is you look at the distance between x and y to the p, and then you integrate it over all possible measures, which are couplings of nu1 and nu2. Another way to write this in a probabilistic way is to just say that you look over pairs of random vectors where x1 has marginal nu1, x2 has marginal nu2, and you look at the expectation of this. Okay, so the pth sort of LP. Okay, so convergence in the WP metric is actually equivalent to weak convergence and convergence of the pth moments. So that's a little exercise if you didn't know that before, to try and do it. Okay, so going back to the asymptotic approximation theorem. So suppose that for each n, we are given an epsilon n Nash equilibrium. Okay, so that's an to this. And suppose that this epsilon n is going to 0. We want to understand what the limit of this might be. And so this mu n is now the empirical measure of the actions that is taken by this. So it's sort of a Nash action measure, empirical measure, distribution of the actions, or epsilon n Nash actually. Okay, then mu n is relatively compact. Okay, so this sequence is relatively compact, which is not surprising because we just said that we assumed our standing assumption that A itself is compact. And so we know that this whole space is compact. So of course, any subset of it is also relatively compact. That is nothing surprising. You can, of course, I'm just taking the simplest assumptions, which are still enough to cover a wide variety of examples. But of course, you could look at more general A, and then you just have to do a little more work and put some conditions under which you would have relative compactness of this. But the interesting thing is, what does it converge to? Any weak limit point mu of this, so is such that the support of mu, so is this. So what is it saying? The support of mu is going to be all the sets of actions that maximize when you use mu, such that you look at all the actions that you get the maximum. So you want to think of mu as sort of the empirical measure of all the other players in the system, right? And you want to say that's what you're sort of seeing, and then you are one player who is now doing this optimization, which is trying to choose the best action for yourself. So obviously you have to choose the action that maximizes this over all A. And the mu itself, so it's of course a recursive definition, right? But the mu itself will put only support on those kinds of A's. So there's no, I'm not saying anything about there being a unique mu, but I'm saying that any mu, this weak limit will be such that the support of mu has to be, that when I am the mu, then I will only put supports on those that when I use mu, I'll be maximizing myself. Is this clear? For n-player games? No, this is saying if, this is a very good question, saying if we are given epsilon and Nash equilibria. So you might not even have epsilon and Nash equilibria, let alone Nash equilibria, okay? So of course that's something that Nash realized back in the 60s or 70s. So in that case, what you have to do is you have to actually look in terms of mixed strategies. And then you can do all of this with respect to mixed strategies and see what the limit is. And it's much more complicated, so I just looked at the pure case. But I will talk a little bit about that later. So what he's asking is, do you know that there will always be an epsilon and Nash equilibrium, or do you know for a game, right? So the point, yes. Are you asking in the limit? Yeah. Does there, I'm going to talk about that. Yeah. You're not talking about are you talking about the n-player equilibrium or the limit? Both, yeah. But anyway, this is a point that in the n-player, you may not have a Nash equilibrium, but, so there's that question. But it turns out that you will always, in many cases you have, and some problems you don't, but all this will go through if you generalize the notion of strategies to what are called mixed strategies, and then everything goes through. It's just that everything is more complicated, so it's not the best first thing to start with. Okay? Yes, Harsh. Yeah, please. So, no. So what does it mean for the weak limit to be a Nash equilibrium? Well, is a Nash equilibrium for which game? What does it mean to be what is the limit game? Okay, first, the Nash equilibrium is a collection of A1 to AN. It's not just one action. Is that what you mean? Okay. Here, you can ask the question, another one, but
I'm trying to make sense.
Yeah, but these are actually good questions because, you might get the answer next, but first it's good to ask the questions. Yeah, that's really what we're trying to do. We're trying to see what is the analog in the limit of a Nash equilibrium, right? And that's what we're trying to define here, if that's what you're asking. Yeah. So this thing actually gives us some insight into how to define that. Okay, so I'm going to come to explain what that is. Yes? Right, so it doesn't have to be, it doesn't have to be greater than this, but it can be greater than that minus some epsilon. So that each person can unilaterally only get a gain of changing his person at most epsilon. Is that, we're going to talk about all those things. This is all we know so far. We're saying there's convergence of some sort. Of course, you can take epsilon equals 0 in this, if in the case when you have Nash equilibria, and then it tells you that limits of Nash equilibria have this property. That's all we've been told, right? So subsequential limits. So then, of course, you want to try to investigate when these, so you know compactness, so you know everything is compact, so this is relatively compact, so you know there's a solution to this, right? Because you're just told that the subsequential limit exists, and that would be this, right? So existence is not a problem, yeah? But, which as usual, for limit theorems, the existence is not a problem, but the question is if you really want convergence as opposed to, then you would want to know when it's unique and when it's not unique, and questions like that, right? Okay. Because the standard way to prove convergence is to first choose relative compactness, then characterize the limit. Then if you can uniquely characterize the limit, then you get convergence, right? So, of course, like I said, since A is compact, the tightness of mu n is automatic, and Prohorov's theorem says mu n is relative. And now let mu A, but I have to prove this theorem to you, right? I just stated it. So the first part, as I told you, is trivial. So now I'll give you the proof. I thought it's better to do the proof on the board, or you'll have to refer to equations in the previous slide, which are not accessible. So just tell me if I'm not writing large enough or you can't see, okay, because I don't know what this room is like. But, so I'll write there. So let me tell you how the proof goes, because it's important to sort of understand. Though it might be intuitive, it's sort of what are the elements of the proof. Okay, so proof. So you know that since an, let's say an is this a1 to an is epsilon n Nash. Can everybody see? Is it clear? Okay. Then for each I equals 1 to n, you have f of ain mu n is greater than, of course, f of b, where I'll define this, but you know what this will be. It's just substituting my ai by b, right? Where mu n ib is simply the measure I'll get by taking mu n but removing my delta ain. Right, so this is just switching the strategy of the ith player to b. Is that clear? Is this clear? Okay, so this is just the empirical, what would be the empirical measure if I switch the strategy? Okay, but now I can average this inequality here over I equals 1 to n. And then what do you get? You say, okay, I average over this action space. I'm going to just get f of a mu n dA. Right, is that clear? So this is just a sum, right? This is just that 1 over n sum of that. And that's just going to be greater than or equal to, so let me write this just for clarity. So let me write this way. Yeah, I know. So of course, right, for any b. Is that clear? Okay. So now what would you want to do in particular if you take a subsequential limit, mu n k, which converge in the tightness, because we know the mu n's are subsequent. In particular, it will be true for any subsequential limit which is converging. Is that clear? So, and mu n k, a converging subsequence, Is that clear? I mean, it's true for all n, it's true in particular for those. So now obviously what you want to do is take limits as n goes to, k goes to infinity, right, to see what happens. And assume subsequence converging with limit, weak limit mu. Okay, so it's a subsequence that's converging with the weak limit mu. And now I want to send k to infinity, and I would like to see what the limits of both these. So goal, identify limits of both sides. So what's the limit of the LHS? So I'm claiming that I can replace both of these by mu. That's what we would want. But why can we do that? So, right, pardon? Right, F is jointly continuous. So of course, there's a little bit of a theorem, but you could, exercise. So this is clear for joint continuity. It's clear that this will happen by joint continuity and the definition of weak convergence. Okay? And then the other thing for the right-hand side, do not cross. Okay. I will do the right-hand side on the left-hand side. So, okay. So for the right-hand side, what we want to do is we first note that the joint empirical measure, we need to sort of look at this difference, but that's obviously vanishing. Right. So what we do, and this is a very, very standard thing that happens in mean field, you sort of couple two different strategies. Okay, so here what we're going to do is couple the original strategy, so which was the one with A, and then the one when you had the AI replaced by B. Okay, so what we're going to do is when it's given by, so this is why you have an A cross A empirical measure, which is given by 1 over n summation k equals 1 to n, k not equal to I, of delta A k n and A. Right, so this is just, these were all just the same. Okay, plus 1 over n delta. Right? This is the joint strategy empirical measure. Right? So the first coordinate is of the original one where we don't change the AI. The second one, it was all the same except for AI, we changed to B. Okay, but this is a coupling of mu n and mu n b. Is this clear? All it means is that the first marginal is simply giving me the empirical measure mu n, which is obvious, because it's just, and the second marginal is giving me mu n ib, just by definition, right? Because it's the first one minus delta akn and plus delta b. Clear? Yeah? That's the coupling just means this is a probability measure whose first marginal is mu n and its second marginal is mu n ib. Okay, on A cross A. Okay, so then, hence you can bound the Wasserstein 1 distance is less than 1 over n, right? Yes, sorry. Thank you. Okay, because what's the difference between these two? It's just the delta. Okay? But we're in a compact state space, right? By compactness of A, this is bounded by some c less than infinity, right? So this goes to 0. right? As k goes to infinity, I guess. Yeah, but as n goes to infinity. Okay. So, okay. So now we just have exercise. We know that if A is compact, we're given this, and now we still have that integral. But then again, you use the uniform continuity. But just to give you the details for the first, PA is compact, and F is uniformly continuous, because we assumed continuity, so it's obviously uniformly continuous on a compact state space. So this implies that lim of the soup over all possible actions of this difference for any of the players yeah. Any questions? Okay. So yeah. And then since epsilon n goes to 0, we have limit of k tends to infinity of 1 over nk. So even though this is probably the simplest setting, you at least get some idea of the general techniques using coupling arguments. So this implies that integral a f a mu dA is greater than f b mu, right? Just taking the limits of that right-hand side and using this fact, right? And you know that uniformly, you have this uniform convergence. Is this clear? Okay, so once you have that, then this is true for every, since it's true for every B, it's also, I can replace this by soup B, since it was true for every B. And so, but we have trivially, we know that F A mu is less than soup B F A mu, F B mu, sorry. Right? Just taking the max, and you have this. So this, from these two, it's clear that mu can only be supported, okay, on those which are actually maximizing. Okay, is that clear? Because otherwise you'll get a contradiction. Okay. Just 1 second. Okay, somebody had a question? No, it's a common. Everybody has the same action space. Yeah, well, I'll come to a generalization shortly, which is important actually for the congestion game. But that's why the first is the vanilla version of the static game to see what the limit would look like. Okay? Yeah, everybody has the same action space, same functional dependence of the objective function. Okay? Yeah, any other questions? Yes. This. Well, I have, this is less than or equal to this. If there's some point over here which is strictly, which this puts, this cannot put support on anything where this is greater than, right? Because this is the soup. So if it actually puts support on something that's strictly less, okay, then your integral is, this thing will be violated. Right, so if you, this is a good little exercise, it's 2 minutes to see, just do an argument by contradiction, right? Because you already know that the integral has to be equal. From these two, you can also take just the integrals. So these two things have to be equal, okay? Just from that, you can tell. Because you're just integrating with respect to a probability measure. So, okay. Little a, yeah? Yes. Yes, yeah. Yeah, here I'm just doing all the compactness. Otherwise, you need just more tightness estimates. That's it. I mean, you can generalize. But in all of these, I mean, typically you can, then, you have some conditions on the F, you can still show compactness with tightness. For instance, we're going to do it in more general cases with diffusions, which live on R, RD, and there's dynamics. So compactness is just so that you get the whole main idea without getting bogged down in estimates, right? But it's not usually, it's just a technical simplification. It's not a fundamental limitation, okay? Okay, so you get some idea of this proof. I hope that was clear. But this tells us that we remember where we were, all the questions that we had just before I gave you the proof, which was, okay, but we want to sort of have a limit notion of a Nash equilibrium, right? But this is telling us that this is what the notion should be. So what you'd say is a probability measure, or mu, is called a mean field equilibrium. It's sometimes in this static game context also called a Cournot-Nash equilibrium. But it's called a mean field equilibrium if, in fact, its support satisfies this. So, right, this is the same thing that was just the property of the limit that we saw, that it puts all its support on the maximizers of F, okay, when it itself is the background. Okay, it's clear? Okay, so yeah, so this is what I said in words. And why is it intuitively, what do you want to think of this as? I said A, you want to think of as a player in a continuum game where there are many, many players. And it represents the action of one of the agent among a continuum. And so that action, of course, because it's a limit of a Nash equilibrium, should be doing something that's maximizing this. And in the continuum, no single agent can influence mu by changing the actions. So hence you have this optimality of the typical agent. So that's sort of the intuition. But anyway, we proved it. Okay, so now we want to understand when does mu n actually converge to the mean field equilibrium. So you want some conditions on monotonicity, for instance. And it turns out that if you have this, if the F that we had, which was our objective function, has this, so M1 minus M2 is just a signed measure. And so for any M1 M probability measures that are not equal to each other, of course, if they're equal to each other, you can't have a strict less than, right? But if they're not, if they're distinct, then you want this difference to go with the same sign, or rather opposite sign from M1 minus M2. Okay, then there is at most one. The proof is very simple. So remember, this was the condition. Well, so that there is at least one from the fact that there's a limit. And the limit satisfies that.
No, the epsilon n is the assumption. If you have epsilon n for every...
Yeah, you mean, yeah, I am assuming there are epsilon n Nash equilibria. Yeah, because I'm saying otherwise I can do the whole thing in mixed strategies and have a different, yeah. So for now, just saying, look at games where there are epsilon and Nash equilibria, and then you want to understand what's happening, right? If there aren't, then you can do all of this in this. So I've given references at the end for those who want to look. There are some nice notes of Kardialage and some other people, so.
Like is that...
So there are many examples where it's fine, you can get them. Like I will tell you these potential games where you will have them. But there are examples, I mean, yeah, Nash, they're not. So you do want to consider mixed strategy games, certainly.
Similar flavor of the technique.
Yes, the technique, it's just that everything is on probability space and different tightnesses, you know.
So then the actions are probability measures.
Exactly, so it's just...
It's also on compact spaces, you do similar.
Similar, it's very similar. In fact, it's very parallel, so. And then this definition, which already has this recursive structure, right, this thing, will be more complicated. Because it's mixed strategy. It'll be more confusing, and so I didn't think that that would be the best start. Okay, so this is a very simple thing. You know, if M1, M2 are distinct, then you must have this just from the fact that you are, if you take an M1 and you change your M1 and your M2, then you'll have to have a greater than or equal to 0. Whereas if you take your M2 in both cases, you have this, I think I should have done, this should have been an M1 and these two should have been M2. Sorry, I'll change that. But then if you take the distance, all I'm just saying, if I change my measure, right? So because of the fact that you have FA_M1 minus FA_M2 has to be positive. So you're going to have this greater than 0. On the other hand, FA_M2, if you change the M2 minus M1, it also has to be greater than 0 because of this. So then this implies that if you just take the difference, you're going to have this. And then in light of 1, this leads to a contradiction of the assumption M1. So it's actually just a 2-line proof, it's not. And okay, but then how restrictive is this? Here's the class of potential games where actually you get this monotonicity assumption translates into a condition on some concavity of a certain potential function. So let me tell you what these potential games are, because a class of congestion games are in fact potential games. So remember, this was the monotonicity condition. And suppose A is finite, for instance, with cardinality some D. Then PA, of course, can be identified with a D-1 dimensional simplex, right? And now suppose you have a function G on this simplex such that, it's this should be gradient, not Laplacian. Gradient of G is F1 to Fd, where what is this F1 is just, I'm fixing the player now and just looking at it as a function of the measure. Okay, so fixing the player and looking at it. Then G is called the potential function and the corresponding game a potential game. So the details are not too important except for the fact that you assume something else about the form of the payoff function. Right? You're just saying how the payoff function depends on the players and measures. It's got as a gradient of some other function G. Okay? And if you can do a little exercise, if G is strictly concave, then the monotonicity condition holds. So here's just to tell you that it's verifiable in certain classes, in other cases it's not. The monotonicity condition is definitely not necessary for uniqueness. So I'm just giving you one example where it's uniqueness, otherwise you have to do many other things to see whether it's unique. Okay, and many times it may not be unique. So any questions about this before I move on to the next? Okay. So many times it may not be unique, and you might say, okay, if there are many ones, then are we getting spurious solutions in the limit which have nothing to do with the original, right? We know that, of course, all the originals are contained in the limits, right? So, of course, you could have the n-player games themselves, which are definitely non-unique many times, right? Again, unless they're these potential games with certain structure. And then it could be that as n goes to infinity, that non-uniqueness goes away, or it could be that it persists, right? But you might want to ask the question, is this MFE equilibrium really a good notion of solution, or does it also contain all sorts of extra equilibria which would not arise as limits of Nash equilibria? And this theorem says, does the MFE truly identify the limiting behavior of n-player or not? And this says it does identify. So it says if mu is an MFE, then there exists epsilon greater than a sequence of actions AI such that limit epsilon greater, and the weak limit of mu n is mu, where mu n is this. So here's a way to say that in some sense, if you want to know if there are at least epsilon n Nash equilibria, then if you can prove existence of this solution to this MFE without thinking of it as a limit, not assuming the existence of epsilon n, but just the problem itself, then you know from this theorem that you can actually construct epsilon n Nash equilibria. Right? So if you can independently analyze the existence of solutions to the MFE, which can be done in some cases, then that in fact implies existence of epsilon n Nash equilibria for the prelimit. Okay? Okay. So I will maybe give this proof later, first sort of tell you the big picture and then come back and give you this proof in the interest of time. Okay? Okay. So one caveat, remember here I says I can get an epsilon, I can find epsilon n Nash equilibria, but here I never said I can actually find Nash equilibria themselves. So it's not true that every limit of the mean field is a limit of Nash equilibria. It's only a limit of epsilon n Nash equilibria with epsilon n going to 0. Is that clear? So that's the caveat. The theorem is false if one requires epsilon equal to 0. Right? So the mean field equilibrium, there may be more equilibria, mean field equilibria, than limits of just Nash equilibria. Because they may contain also limits of epsilon n Nash equilibria, which are not necessarily limits of Nash equilibria. Even though it's epsilon n, you might think, oh, they're all, there won't be any difference between epsilon n. Here's an example so that you see it, a simple example, trivial one. So A is just the interval 0, 1, FAM is just A times the mean, okay, of the measure. And so claim, you can see that delta 0, and M equals delta 1 are the only mean field equilibria in this case. Okay, so here's sort of, what does that mean? well, look over here, A delta 0 is 0 for all A, right? If I have a probability measure which is concentrated on 0, its mean is 0. So obviously f of A is 0 for all 0. Okay, so which of course then implies that in particular A equals 0 is included in that. And so certainly delta 0 is a mean field equilibrium. So you're sort of seeing how you can check with this recursive definition, you can still analyze it. Also FA delta 1, so if this is delta 1, if it's all 1, then you can also see that is just A, and that's maximized when A is 1. Okay, that's clear. Here, obviously A is maximized on 0, 1 when A is 1. Okay, so it's a trivial example. So both of these are MFE, and you can show that if this M bar is anything less than 1, then M cannot be supported on 1. So there are no other MFE. You can just, simple argument. So this delta 0 and delta 1 are the only MFE. That's the claim. But only M equals delta 1 equilibrium arises as the limit of n-player equilibria. Why? Because in this game, with this n-player equilibria, you can easily check that the only Nash equilibria for the n-player game is all of them being 1. Okay? And so that tells you that the delta 0 does not arise as a limit of Nash equilibria. Okay? But we know, of course, from the theorem that it does arise as a limit of epsilon n Nash equilibria, which is somewhat surprising, right? That you're sort of, you think you're close enough, you think maybe my action has to be close enough to 1, but in fact it doesn't. Okay, so you can be close enough to epsilon n and you can still get a limit. Okay, okay. So just to tell you that non-trivial things happen, but epsilon n Nash equilibrium. Okay, so now you asked about existence. So in this particular case, you can show that given the standing assumptions that I said on F, in fact, you can independently check that there exists an MFE, not assuming now that there are n-player Nash equilibria. So in fact, when combined with the previous theorem, this shows that you actually have epsilon n with these Fs, right? But you can have other Fs and more complicated, maybe not a compact state space, etc., where you will not have the n player. You asked this question, right? So at least here you know that you have epsilon n Nash equilibrium.
The zero case, you show us what the epsilon is?
No, not now, but that's an exercise, but try it out. It's a very simple example. Yeah. But I can show it to you tomorrow, but let people think about it. Yeah. Okay, and the key, this is just a key ingredient of the proof, is simply Kakutani's fixed point theorem. Again, this is a standard way in which mean field arguments are. So first, to show convergence theorem, there's always typically some kind of coupling argument. And for existence results, then you have some sort of fixed point argument. Okay, because remember, it's kind of recursive in terms of you look at the empirical measure, and then you want some property about that empirical measure to be satisfied. So you can start with any background measure and then see what its support is, right? And then sort of try to iterate and see what happens. So maybe I can give the proof of this. Okay. Okay. See, this is not as probabilistic. So, okay, I'll give the proof again at the end. Okay, so depending on how much time there is. Okay. In this case, I'm not even writing AIN. You might think, oh, there's a triangle. Yes, in this case, I mean, in general, you want to say there would be AIN, that would be enough, but I'm saying something even stronger.
Yeah. You could have say AIN.
They could be changing, just an array, right? You would want an array of actions, but here you could actually just choose AIs. And I'll give you the proof now, because I'm sort of, because the proof of the other one with Kakutani's fixed point theorem is not as, I mean, it's sort of an analytical theorem. Essentially, what you need to prove is something is convex and something is compact, right? So it's using some Rees representation theorem. So it's quite standard in terms of the techniques that you're using, just specific to this problem. So I'll give you this proof. Okay. So what I'm going to do is I'm going to first start with xi's. So let's say I fix first mu, which is an F. Right, we start with knowing that we have some mean field equilibrium. And then I'm going to take xi IID with distribution mu. Okay, so they're action valued, defined on some probability space. And now I define the empirical measure okay, so now of course we know that and then for A and A, I'll define the replaced as before. I'll define mu n IA to be mu n minus delta A plus 1 over n delta A. Okay, is that clear? Just the usual empirical measure if I changed. Okay. And now, what do we expect mu n to converge to? Yeah, so the law of large numbers tells us that. So I'll write this for. So these are, of course, random measures, but almost surely they will converge by the law of large numbers, right? So, okay, so, I mean, there's a small thing that I'm using here. So let me just say, essentially, just to be, you know that integral f d mu n is simply this. So of course, the law of large number only implies that for every f in CB of A, that you have almost surely integral f d mu n is equal to expectation of fx1, which is simply integral f d mu, right? But that's not what we're saying. We want the probability that these things converge to be 1 for all f. So, but we want to say, in fact, we have probability that limit n tends to infinity of integral f d mu n right? So it's just about the null sets. The point is here it's okay because CBA, since A is compact, this is separable. So it's enough to check for countably many functions. And so you can put the f's inside. Because otherwise you have to be careful in general. So you can do this. But in fact, you can do this for much more general A. But there the proof is more, even when this is not separable. But okay, you can look at Parthasarthi's book if you want to see how that's done for more general A. Okay, but we have A compact, so we get away lightly. Okay, so now you next define the random variable. Okay, so this is just looking at this mu n IA and then minus mu n. Okay, so clearly we know that epsilon is greater than or equal to 0. Is that clear? Why? Almost surely. Remember, epsilon n is a random variable. Right, this is just because it's a soup overall A in A. That's right. Okay, and also the definition of this by swapping. Okay. So, and by construction, x1, xn is an epsilon n Nash equilibrium, almost surely, for each n. Is that clear? Mu n IA is here. So it's mu n plus 1 over n delta A minus delta xi. So I'm just...
We have changed this before. When we compare mu n and mu n IA, that's
yeah, you have to do it once with that, and then you do a plus minus, and you'll see both of them are positive. Yeah, so it's not... Yeah, yeah. Exactly, it's from you're using the definition of MFE here.
yes,
Yeah, Okay, bye. So, thanks. Yeah, so that helps clarify. Okay, so now, so it suffices to show, I claim that it suffices to show that epsilon n goes to 0. Why? Suppose I can show that epsilon n goes to 0. Then I can choose some realization, okay, of the xi's, okay, for which some omega, for which mu n omega goes to mu, and I take that xi omega and I set A to be that xi omega. And that's what we're going to get, okay? Because then we can choose, almost surely, because then we can choose some realization omega, so realization okay? So we get the sequence AI is just from that realization. Okay, so now we want to show that indeed that epsilon n goes to 0. Okay, I'm making repeated use of uniform continuity and the convergence of mu n to mu. Note that if we define, I'm going to now replace the mu n by mu in some places. So if I define epsilon tilde n to be the max of over all the players of just the soup of f of a mu n minus f of xi mu n, which is also obviously, which is clearly a positive thing, right? But the difference between that and that, since mu n ai converges to mu weakly, right? Because the difference between that and mu n is just some 1 over n thing. You have limit, and I'm using the uniform continuity of f everywhere without repeating that everywhere. Epsilon over epsilon tilde n is equal to 0. So, in other words, to show that epsilon goes to 0, it's enough to show that epsilon tilde n goes to 0. Okay, but it's sort of clearer why epsilon tilde n, because we'll again use uniform continuity of f to show that limit as n tends to infinity of the max of soup minus the soup, if I'd replace the mu n's by mu, okay, here just, you can think of, you're just sort of adding and subtracting the different ones, so, okay. And to conclude the proof, you simply note that mu being an MFE and xi being distributed according to mu, this implies that soup A in A, f of A mu, is equal to f of xi mu almost surely. Right? Almost surely with respect to mu. So, is that clear? And so you combine all these inequalities. So, I just recall that this meant that mu of A in A, such that f A mu is equal to soup B in A f B mu. That was the definition. Maybe it's there. So, okay. So anyway, that if you put all these combine that inequality and this inequality, you get that the epsilon tilde ends goes to 0, therefore epsilon ends go to 0, and then we can construct the sequence AI. Okay, so I think I'm done. Yes. So